Good afternoon, everyone. Thanks for braving the heat, and it's wonderful to see so many people here. My name is Raphael Busso. It is an honor and privilege to introduce my colleague, Geoff Penington, who is going to be giving our colloquium today. Geoff got his PhD under Patrick Hayden's supervision at Stanford, and we hired him very smartly, I should add, straight out of grad school. And very, very happy to have him here. Geoff has won a lot of prizes, too many for me to memorize them all, but the New Horizon Prize is one of them, and most recently the George E. Valley Prize of the American Physical Society. I'm a big fan of gravity. Gravity is just the best force, and it's been at the center of a lot of the important scientific developments since really ancient times. The ancients, when they studied the motions of the planets, they didn't know it, but they were studying gravity. Kepler came up with much simplified description, but they already had mathematical laws for it. And then, people like Galileo, well, he was experimenting with how things actually fall. Newton had the insight of putting those two things together, the celestial and terrestrial, and say there's one law for both of them, like maybe the biggest single step to me in sort of scientific progress. Einstein told us, well, it's not a force at all. It's things trying to go as straight as they can in a curved space-time. And so I think gravity must have felt a little bad when there was one revolution, the discovery of quantum mechanics, in which it played no role. And so he came back 50 years later and informed us that, in fact, it already knew about quantum mechanics. You can study gravity, as Bekenstein and Hawking did, and it'll tell you how many quantum states a black hole has. And people didn't figure that out by knowing what the analog of the atoms are. They didn't figure this out by having a black hole in their lab that they could heat up by a degree and figure out how much the entropy changes. They asked the classical theory, the so-called classical theory, and it gave them the answer, right? And later in the 90s, we discovered this idea of the holographic principle. Gravity also knows about the quantum states of matter, even if we still don't know what the fundamental ingredients are of matter, right? More recently, 10 years ago, maybe here at Berkeley, we were able to use gravity to discover new things about quantum field theory that have since been proven. Well, Geoff has taken this to a different level, one that I personally did not think was possible. And this includes asking a black hole whether it'll return the quantum information you throw in it, showing that gravity thinks like an engineer and sends information around in a quantum error-correcting way and in a way that corresponds to certain sophisticated quantum communication protocols. None of those things I would have ever thought possible, and I look forward to the colloquium where he's going to tell us more about that. So take it away, Geoff.
Okay, so thank you very much indeed, Raphael, for that. I think the traditional thing to do in a colloquium is to try to take as many of your papers as possible and weave them into some narrative about how you're going to solve all of physics any day now, at least in 5 years or so. This colloquium is not going to be terribly like that. It's going to be about a load of stuff that was already known in the 1970s, and then about one paper with these people. Ooh, my laser pointer is gone. There we go, including Luca Liesti, who's also a professor here. And that one paper isn't even out on arXiv yet. So it's maybe an unconventional way to do things. I'm doing it for a few reasons. Firstly, maybe I got bored of doing theory and wanted to do something experimental. Secondly, this paper originally started, the first work on it, I think, happened in the summer of 2020 during COVID, which, as Raphael said, was when I first joined Berkeley, so it feels somehow fitting to give a colloquium on it now. But mostly because I just think it's a very fun story, and it's a story that captures a lot of how theoretical physics research works. And it's also a story that at the end of the day boils down to how well did you learn your undergraduate quantum mechanics courses and perturbation theory and stuff like that. So the fact that it's taken us 4 years to do maybe tells you the answer is not well enough in our case. But yeah, it's a very fun story, and it's answering a very simple question very basic and fundamental question I wanted to phrase the whole talk about, which is arguably the simplest question of all, everything involving gravity. Let's take a universe, let's take the most basic ingredient of general relativity, a black hole. Let's have the universe contain nothing other than that black hole, and let's just ask what happens next. And it's going to turn out that this is an extraordinarily interesting question that has an awful lot going on with it. I should add a few qualifications here about what the universe is. So it's sometimes the accusation is occasionally made that people in quantum gravity believe in studying every universe other than our own, whether it be universes in anti-de Sitter space with a negative cosmological constant, universes with different number of dimensions, 10 or 2 or whatever it might be. This is generally going to be in our universe. It's going to be a universe containing the standard model in gravity. The only thing I'm going to do is I'm going to turn off all cosmology, because some of the stuff happening in this universe, this black hole, is going to take quite a long time, and cosmology sort of gets in the way of that. So we're not going to worry about dark matter or dark energy or anything, but it will be the real particles that we have in our universe and general relativity. And we're not going to be asking sophisticated questions like the ones Raphael talked about whether information comes back out if you throw back in, sort of things that you have to probe in very subtle ways. We're going to be asking very, very basic questions, like what particle gets emitted from a black hole, what will their energies be, stuff like that. But it's going to turn out, somewhat remarkably, I think, this is something I didn't appreciate at all until this project, that for a generic, sufficiently large black hole, then even answering those very basic questions is going to require us to do fully fledged quantum gravity calculations. And by that I mean, if you did the sort of stuff that Hawking was doing 50 years ago and people like that, where you treat gravity classically but everything else quantum mechanically, you will get answers for these black holes that are almost always wrong. We're going to be able to get them almost always right, and we're going to do that despite not fundamentally knowing how quantum gravity works. Okay, well, we're going to start sort of with the very initial dynamics of the black hole. So here is my black hole. You can see it's black and it's a hole. And we're just going to ask what happens to this black hole classically, because generally, classical general relativity is going to give the sort of fastest, earliest dynamics. So in the late 1960s, early 1970s, people began to understand that any black hole, no matter what you try to do with it, no matter what you make it from, no matter if it's wobbling around or merging with some other black holes, stuff like that, if you leave it sit there for a little while, it will quickly settle down to an equilibrium solution, like most things do in physics. But it's a very, very simple equilibrium solution. It's characterized only by 3 things. By the mass of the black hole, how much energy it has, by its charge. Here it's electric charge. In principle, it could have a magnetic charge, but that would require magnetic monopoles to exist, so we won't worry about that. And by its angular momentum, how much that black hole is spinning. That's conserved, and if you start with spinning stuff, you'll end up with a spinning black hole. I should say a minor qualification here. Mathematicians would still not believe this to be true. I think there was a couple of years ago, there was a 2,000-page long paper that proved that if you start very close to one of these solutions, you do actually get to one of these solutions. These solutions are stable. I think they still wouldn't accept that if you start with some generic out-of-equilibrium thing, you get to this. But at a physicist's level of rigor, this has been settled for a long time. So generically, you end up with a black hole whose charge scales comparably to its mass. Its angular momentum scales like its mass squared. Of course, this is all classical. So classically, this is just the end of the story. It settles down and it remains there forever for all time. Of course, we don't live in a classical universe. We live in a universe with quantum mechanics. So in the early 70s, people would have said that this is all correct up to very, very tiny quantum corrections that presumably don't change the qualitative story. It still just settles down to equilibrium, but it will have some tiny, tiny, tiny corrections to that equilibrium solution. Nonetheless, in 1974, for various reasons I won't get into, Hawking went ahead and calculated those boring, tiny quantum corrections. Now, as I said, at the time, we didn't have a clue how to do quantum gravity properly. We still don't at a fundamental level. And so he did the next best thing. He said, okay, gravity is the dynamics of space-time, of the geometry of space-time. But in the case that we have a really big black hole, the space-time's really big, it's really classical looking, and so it doesn't matter if we just treat that classically. What we're going to do is we're going to treat that classically, but then treat everything else quantum mechanically. In particular, we're going to treat all the fields in our classical space-time as quantum mechanical objects. Those fields include electromagnetic fields you'd learned about in undergraduate classes, but they also include other things that you might learn about in a quantum field theory class, like the electron field, the electron field, quark fields. Basically, for every fundamental particle you've heard of in the standard model, you have a field. And we're going to treat all those fields quantum mechanically, even while treating the space-time classically. So this is called doing semi-classical gravity, and it can work very well in a lot of circumstances. In particular, Hawking found something very cool by doing it. What he found, and I think he was the first person to see this, though it really doesn't have anything to do with black holes, is that you look at quantum fields very near the horizon of the black hole, then you'll find that they're entangled with one another, meaning that you can't talk about the state of just these fields slightly outside the horizon or just the fields slightly inside, because they don't have well-defined states on their own. They only have a well-defined state when you look at both of them at once. Okay, this is this very special feature of quantum mechanics that couldn't exist classically, and it's just true everywhere in the universe all around us. There's nothing special about the horizon. In particular, if you're an accelerating observer very near the horizon of the black hole, or very near anything else, you'll see a temperature. You'll see a temperature, you see that these fields look like they're thermal, like they're thermally excited and not in the ground state at all. So this is the so-called Unruh effect. It was only discovered after Hawking's calculation, but really it should have been discovered first, because it's a simpler thing, and Hawking was really using it. But again, it's just a thing about quantum fields, nothing to do with black holes. The interesting thing about a black hole is the dynamics of a black hole mean that fields outside the horizon can escape off to infinity. They can propagate through space, just like electromagnetic fields do when we solve for photons and so on. But fields inside can't ever get out. That's basically the definition of a horizon. They're always stuck inside. And so this separates, as this field goes off to infinity, this short-range entanglement between stuff just inside and just outside gets dragged out. It gets stretched across the entire space-time, and you end up with these fields outside escaping off to infinity and becoming actual, genuine thermal radiation that you'll see even if you're not accelerating. They're a real physical thing that carries real physical energy. So this was really an extraordinary calculation by Hawking. It's one of my favorite calculations in all of physics. And one reason why is I've given here the formula he came up with for the temperature of the black hole. It even has it down to a T. It's not just some approximation. And even though it didn't involve quantizing gravity itself, it did involve all the fundamental fields in physics in just one single calculation. It was arguably the first calculation to ever do that. You can see that just by looking at this formula. It has a reduced Planck's constant in there, an h bar. Means that it is inherently a quantum mechanical calculation. It has a speed of light cubed, so it's a relativistic calculation. It has gravity getting involved. It's a Newton's constant. It has thermodynamics getting involved. There's Boltzmann's constant in there. And there's a pi getting involved, so there's some circles showing up somewhere too. Okay. So there's this thermal radiation going off to infinity at this temperature. And thermal radiation carries energy, and energy is conserved. So that means that the black hole must be losing mass, right? If energy is going off, and the total energy stays constant, then the energy left of the black hole has to be going down. So this is an extraordinary discovery that just says this classical picture of the black hole remaining there for all time is just completely wrong. It's a very slow effect. That's the sense in which it's small. If you just wait for a little bit of time, you won't see much change to the black hole. But eventually, it will get smaller and smaller and lose energy and totally evaporate. Okay, so that's what happens to the mass of the black hole. Could also ask what happens to the angular momentum, because there's these three things. And the answer is pretty boring. It just turns out there's a lot of modes of photons that can get emitted, right? If you've done a quantum mechanics scattering problems, you'll know that you have different angular momentum modes that go off to infinity. And when you do this Hawking calculation for a black hole that is spinning, then it wants to emit modes that have angular momentum in the same direction as the black hole. So it wants to lose angular momentum. That's sort of preferentially, those modes preferentially get emitted. And if you do the calculation correctly, what you find is that the black hole generally loses angular momentum faster than it loses mass. So if you wait for just a little bit of time, it won't have lost that much of its mass, but it will have lost most of the angular momentum. So for the rest of this talk, I'm going to assume the black hole has no angular momentum. It's not because I'm lazy or don't want to deal with it, it's just because it will have all gone away by the time we get to the things I'm interested in. Okay, so there's one more thing describing this black hole, and that's its charge. And there's a difference between charge and angular momentum, and that's that even massless particles can carry angular momentum. A photon has no mass, but it can be set off in some mode that's rotating around the black hole. It also carries spin, so it can carry away angular momentum, but it can't carry away charge because it's neutral. Well, all the things that can carry charge, all the charged particles in our universe, are massive. And massive particles, if your black hole is very cold, you saw the formula earlier as the temperature of the black hole is 1 over the mass, massive particles aren't going to be excited at that temperature. Right? The amount of energy needed to create a massive particle is proportional to its mass. If that energy is much higher than the temperature of your system, you're not going to create it spontaneously out of nothing. However, it turns out that if you have a strong enough electric field, then charged particles still can be produced, even at 0 temperature, just from the vacuum. This is a beautiful piece of physics that was actually discovered significantly earlier in the 1950s by Schwinger, and other people had anticipated it even earlier than that. And basically what happens is that in a strong enough electric field, an electron-positron pair gets sort of pulled apart out of the vacuum, and then they repel each other and go off. Or they're repelled, accelerated in opposite directions by the electric field, and they go off. So the electric field at a horizon of a black hole, we can just use totally ordinary Coulomb's law. It turns out to work. It doesn't need correction or anything. It's just proportional to the charge of the black hole divided by the radius of the black hole squared. Roughly the radius of the black hole is like the mass. So this gives something that looks like Q over m squared. So we're radiating this neutral radiation. We're losing energy. Charge is staying the same. This thing's going to get bigger and bigger. Eventually the electric field will get strong enough that the Schwinger effect will happen and electrons will be produced. Okay, I should say the electric field needs to get really bloody strong. So nobody has ever in a lab made the Schwinger effect happen, or even come within a factor of 1,000 or so of making the Schwinger effect happen. But in principle, that's what will happen. And then, once it gets strong enough, electrons or positrons, depending on the charge of the black hole, will be emitted. The black hole will discharge itself. The electric field will stay roughly constant. And that's where the charge goes. So we've now explained how all three things decrease over time. And eventually, they all get really small. And basically, you have semi-classical control over everything that happens through this evaporation of a black hole until the last fraction of a second of its life. And the reason that gets out of control is that at that point, the black hole gets really incredibly hot, it gets incredibly small. All these quantum and gravity effects come into play, and we don't really know the final answer. But we know 99.99999% of it, so that's good enough. Okay. So by 1980, everything I've said until now had happened, and people were pretty happy with this story, except for some weird oddities. And the main weird oddity was that information that fell into the black hole didn't seem to come back out in this radiation. So there's a very fundamental principle of quantum mechanics, and actually all the theories of physics we've ever had until this point, that they're basically reversible. So if we start with some information in the early time, and then we evolve our system forwards in time, that information is still always there at a later time, meaning that I can look at the later state and work out what the earlier state was. Okay, it's a sort of one-to-one map between the state of the early time and the state of the later time. And the Hawking calculation didn't seem to obey that, because the stuff that fell into the black hole was just in the black hole. This radiation was coming out from the horizon. It didn't know at all about the stuff that fell in, so it just seemed to forget about it completely. So for the next 30 years, this sort of became, 40 years, this became one of the dominant problems in quantum gravity, because we had these calculations that we were supposed to be able to trust, and yet they gave answers that seemed in contradiction with the sort of principles that we held very dear and had always been true about physics until now. And it was really only in 2019, as Raphael talked about a bit, that we finally understood how to reconcile that semi-classical calculation with ordinary quantum mechanics, and it does. And the answer is basically that there's these very subtle, so Hawking's calculation is fine as long as you only ask simple questions. If you just ask which particles get emitted, how much energy they have, so on, Hawking's calculation is totally right and is giving you the right thing. But to work out whether the information is there or not, you need to ask about very, very subtle observables, very, very complex observables that are much harder to probe. And when you try to measure these observables, then you find that there are large, subtle quantum corrections from objects called space-time wormholes. When you include these effects, you get something consistent with quantum mechanics. So that's a whole fun story, but it's a story that I will not be talking about anymore today. And you know, I was heavily involved with it, so I very much encourage you to read about it in whatever form. It is really a fun and exciting thing. But today we're going to talk about something in many ways simpler, which is that there was a qualification with the argument I made that we had semi-classical control over this whole evaporation. It's a very simple qualification. So there's a fundamental bound on how big, how small the mass of a black hole of a given charge and angular momentum is. This is called the extremality bound. It's just written here. It just says that the square of the mass has to be at least as big as the square of the angular momentum over the mass squared plus the charge squared. So in particular, the mass squared has to be bigger than the charge squared. If you try to just take our usual black hole solution and violate this bound, you'll get mathematical nonsense. You'll get what's called a naked singularity, which is just not an allowed solution of general relativity. Okay, so how does that screw up the nice little story I told earlier? Well, if the black hole has big enough charge Q, then its mass m gets smaller, and its electric field gets bigger. But the mass can't ever get smaller than Q because we have this bound. So we always have that the electric field at the horizon, it looks like Q divided by the size of the horizon squared, which is like Q over the mass squared, which is at most 1 over Q in size. So if my black hole is really, really, really large charge, then even that charge is not enough to have the Schwinger effect get going and start emitting charged particles. So it turns out the required charge is really, really big. This is basically because electrons are very light in Planck units. The Planck mass is very heavy. It's something like milligrams. Electrons do not weigh a lot, so it's easy to produce them. So it's needs to be about 10 to the 44 times the charge of an electron. So an interesting question is whether any black holes that satisfy this actually exist in the real world. The answer is no. But it sort of could be yes. So if a black hole actually had charge that was almost as big as its mass, if it was genuinely near extremal, then it would only need to have a mass a few percent of the mass of the black hole at the center of our galaxy. So there definitely exist black holes that are big enough for this to be true. But in our universe, there's a lot of charged matter around, and a charged black hole will tend to absorb stuff with the opposite charge and repel stuff with the same charge. And so in practice, black holes are all very, very close to neutral. But in principle, our universe is big enough for a black hole something like this to exist. Okay, but we don't need to worry about our universe. We're dealing with a universe with only a single black hole. So let's just assume we start with a black hole that has charge at least that big. Then we can start again asking this question of what happens to it if we wait a long time. Well, it will still lose mass. It will still lose angular momentum. That all goes through just as before. But this time, no matter how close to this extremality bound it gets, then it will never emit charge, or at least the probability of emitting charge becomes exponentially small. So instead, the black hole will just get closer and closer to this bound of having m roughly equal to q. As it does so, well, there's sort of two options to what happens as the temperature. This is some special point. You'd expect something weird to happen to the temperature. Either it's probably going to go to infinity or it's going to go to 0. Turns out it goes to 0. As you get close to this bound, the temperature of the black hole gets really, really, really cold. It's actually given by this formula. It goes as the square root. This q minus m is how close to the bound you are, and it goes as the square root of that bound. But there's a problem here. When this gets really, really small, square root of q minus m becomes much bigger than q minus m. If q minus m is really, really small, then you get your units right. So when you get below an energy above extremality, a mass above extremality that looks like the charge of the black hole times 10 to the minus 3, so at least 10 to the minus 20, 10 to the minus 30, something like that, then the temperature of the black hole gets bigger than the amount of energy it has above extremality. But the energy of the photons that get emitted by the black hole is proportional to the temperature. They're just thermal. Thermal objects have an energy that's roughly equal to their temperature. So seemingly the energy of a single photon being emitted by this black hole is more than all the energy that black hole has available to it by this basic bound. So it just seemingly can't emit anything at all. So this is a clear signature that something has gone wrong. What has gone wrong? Well, when Hawking did his calculation, he had to assume that the geometry was, space-time geometry was completely fixed and it didn't change very much, right? And that had to be true even if these particles got emitted. But we've just shown that if a single particle gets emitted, it changes the geometry hugely. So that's telling us that Hawking's calculation is just totally wrong. Okay, it just doesn't work for this. We need a theory of quantum gravity to do the calculation problem. So this was recognized already by the 1990s. Every 10 years, some famous person would write a paper about it, speculating about what happened and mostly being wrong in retrospect, but they had good ideas. But it was generally seen as much less of a big deal than the information problem, because we knew why the calculation wasn't working. Right? With the information problem, we had this calculation that should work, but gave us something that felt wrong, that we didn't like. In this case, it was just, we can't deal with any of this. We have to give up, come back when we've solved all of quantum gravity, and then we'd be able to get the answer, and it would be something. So that was basically the status as of maybe 15 years ago. This was just a totally impossible problem. But things started to change about 10 years ago. And what happened was something very interesting. What happened was that people worked out the relevant quantum bits of gravity actually weren't so bad to understand after all. We're still nowhere near understanding all of quantum gravity. We do not have a complete theory of it. But what we realized was that if you only cared about some specific set of modes with the actual relevant quantum mechanical ones, then they turned out to be a completely solvable theory, a remarkably solvable theory. And it's actually the same theory that shows up in condensed matter physics. Shows up most famously in this model called the SYK model. Just you take a load of fermions, basically a load of qubits, a load of spins, whatever you want to think about, and you couple them all together in a random way. You just turn on interactions between all of them, you make those interactions totally random, and at low temperatures, you get exactly the same theory. So you might have heard, if you do condensed matter physics, that the SYK model is holographically dual to a black hole or something like that. That's a much fancier claim than I need or care about here. From our point of view, this is just a sort of one of many examples of universality in physics. Right? You have two very different systems, a black hole and a load of random spins. Well, we don't know how different we are because we don't know what the black hole really is, but at least they seem very different. But you go to low enough temperatures and they're described by the same sort of effective picture of what's going on. So how does it work in the context of black holes? Well, we want to do quantum gravity. We want to integrate over all possible space-time geometries, right? That's how we're meant to do quantum mechanics. We're meant to integrate over all dynamical degrees of freedom. But that's really, really hard. We don't know how to do it. Every time we try, we get nonsense. But what we can notice is that most of those fluctuations are pretty heavy, meaning that they have they have some high action to them. And those modes you can basically treat classically. This is a sort of general principle of physics that if you're doing something that only involves low energies, you only have to care about low energy modes. Okay, so all you have to worry about are the modes that become very light, that are so-called almost zero modes as you go to these very low temperatures. There's some set of those modes that are pretty complicated. They'll all have large fluctuations. They will not behave classically at all. It's like some harmonic oscillator with some really low potential barrier. You'd expect a quantum particle to fluctuate wildly in it and not be localized around any particular point at all. But you can solve them. You can solve them because they turn out to give exactly the Schwarzschild quantum mechanics theory, the same theory that shows up in the SYK model and various other examples. Okay. So people, I guess Luca was an early leader in this, sort of towards the end of the, maybe 5 years ago or so, started to really take seriously these sort of effective description as a way to understand the thermodynamics of black holes when they get very cold. And they found that it leads to very large changes. So the formula I gave before, where the temperature looks like the square root of the energy above extremality, that's true if you don't get too cold, but at a certain energy scale, turns out to be exactly this scale, you got the paradoxes with the radiation having too much energy, then everything gets changed a lot, and instead you find that the temperature is just linearly proportional to the energy above extremality. So rather than having a square root and the Hawking quanta become way bigger than the amount of energy the black hole has available, they now have like roughly the same amount if you believe the Hawking quanta are thermal. So that sort of seems better, but it like doesn't actually help us because at the end of the day, thermal photons have some energy distribution, right? They basically have a Boltzmann distribution, looks like e to the minus the energy over the temperature. So every once in a while, you're going to get something that's like 5 times the temperature or whatever it might be, and that still has way more energy than the black hole has available, so you shouldn't be seeing stuff like that. So this is not enough to fix the problem on its own, but it's suggestive that maybe if we really do everything right, then we can start to make progress here. So pretty much that's where we were 4 years ago, and the make progress here means sit around for 4 years, get things wrong repeatedly, eventually think we have a right story and the paper will come out in Archive any day now. We've been in that state of Archive any day now for about 2 years, so yeah, there's a lot of things. One thing about working with the real world is that there's a lot of physics around, and so there's a lot to get wrong. There's a nice thing about toy models that you choose what to put in them. Our universe, you don't get to choose what's in there, and you have to deal with it all, and you miss stuff sometimes. So okay, let's try to understand what actually happens when you try to see the radiation coming out of this incredibly cold black hole. So I'm going to start with a slide toy example. I'm going to assume my universe contained a massless scalar field. Okay, so the actual fields it contains, it does contain a scalar field, the Higgs, but it has a mass. So we don't actually have anything like this, but it's going to be illustrative, so we'll do it. So if we were just Stephen Hawking in 1974, how would we do this calculation? Well, we've got to do 2 steps. The first step is the thing I said at the beginning of the talk, where you work out that modes very near the horizon are actually thermally excited. They're at this temperature given by the Hawking temperature. But then there's a second step, which is I just sort of glibly said, and then they go off to infinity without working out what actually happens at all. And that's not always what happens. Sometimes they make it to infinity, sometimes they get reflected back into the black hole. But this is where our first example of everything is just undergraduate quantum mechanics is going to come in. When you actually solve the equations and reduce them to this simplest form, you find that this is just a one-dimensional scattering problem. There's some effective potential. So this is sort of the region very near the black hole where the modes are thermal. This is far away from the black hole where the modes are just freely radiating out into space and they're real radiation. And in between them, you have some effective potential barrier. This is just you solve the actual equations of general relativity, you simplify them, write them in a nice form, and it becomes your usual 1D problem just with a particular potential I'm not going to tell you about. So in general, 1D effective potentials are not solvable, and you'll often hear that this sort of scattering problem is in general not solvable. But in our case, it actually is, because we're at really low temperature. Turns out you can do an approximate analytic solution, and you get some answer. And the answer is that if you go to low enough temperatures, then you get a probability of emitting this thing that becomes really small. So not only is the black hole really cold, but most of the time it's not actually able to emit because nothing can get out and nothing can get in. There's this just barrier that prevents low energy things getting in and out. Okay, so that's semi-classically what would happen, but we don't want to do that. We're doing quantum gravity, we're stepping our game up, we're knuckling down, and we're just going to brute force this damn calculation. So how do we do that? Well, I told you that this sort of physics near the horizon, this like strong fluctuations, is described by this Schwarzschild quantum mechanics. I actually skipped out a couple of things. It also has what's called a 2D SU2 gauge field. That's some fancy words. It basically means the black hole has to be allowed to rotate. There's some ability for the black hole to rotate, and that's needs to be described quantum mechanically as well. And then finally, we have our scalar field that we want to put in. Okay? Meanwhile, way out over here, we have our scalar fields just freely propagating through space. And at leading order, these two things don't talk to each other. There's this barrier in the way that just says they're independent quantum systems, and independently we know how to describe each of them. They're solvable things. This is just free field theory in a curved space-time, actually basically just flat space, and this is some quantum mechanical theory that I'm just going to tell you is solved. But there's a very weak interaction between them because this barrier is finite, and we can describe that interaction perturbatively. Okay, it's some incredibly weak coupling. It's like 10 to the minus 100 or so strength of the coupling. We're getting into some big numbers here. But in principle, there's a coupling between the two, which is basically if some wave comes in from infinity, its source is something that changes the Hamiltonian of the near horizon region and vice versa. So in actual fact, there's some interaction Hamiltonian. Again, this is quantum mechanics 2 probably showing up. You have some Hamiltonians you can solve, and then you have some small interaction you can't solve, where that interaction is something acting on one of them, the near horizon. This is just an operator that sort of describes the strength of the matter field near the horizon, times some operators describing these photons way off away from the black hole. So these are sort of creation annihilation operators, ladder operators, your simple harmonic oscillator, for creating photons far away from the black hole. And we just couple the two of them together. Okay, so this is now something we can solve. We turn to our undergraduate quantum mechanics textbooks. We want to describe radiation into some continuously labeled photon modes, labeled by omega. First order in perturbation theory. How do we do that? It's Fermi's golden rule. Okay, it's this famous formula that you can derive. It's given by this thing. In our case, we have this interaction Hamiltonian. We start with a state where we just have the black hole at some energy, EI. We end in a state where the black hole now has energy EF, but we also have a photon outside it with energy omega. We get some delta function that says energy should be conserved. That just comes out of the calculations. And then we plug it in. We reduce it to some calculation in the near horizon region, sometimes some stuff we know. And this formula for this sort of two-point function in the near horizon region has been solved over the last 5-10 years. I can't remember who did it first, actually, in this case. And what you find is that at high enough energies, so this E breakdown, remember, is the scale where we started getting the paradoxes, then basically this sort of quantum calculation almost exactly matches the semi-classical calculation. Everything just works the way Hawking would have said. But then you go to very low energies where the semi-classical calculation made no sense, and instead we get this beautiful curve where it will emit a photon with low enough energy, but it never emits something that would make it go beyond extremality. It's some nice smooth curve that just says, I know I can't go beyond that point. Okay, so that's great, but as I say, we're doing the real universe here. We're actually doing physics properly. So we don't have a massless scalar, so what do we have? Well, what we have is we have photons, which is spin 1, and we have gravitons, which is spin 2. And again, semi-classically, you can do this calculation. It's a load of work. But it turns out at low enough temperatures, then there's sort of two modes, two ways of emitting radiation that are the most important ones. The first one is a photon mode that carries angular momentum 1. The second one is a weirder thing that has a fun name, so I'm going to call it that. It's called the graviphoton mode. It has angular momentum 2, and it's sort of a superposition of a photon and a graviton. This has to do with the fact that the black hole is charged and the photon is the excitations of an electromagnetic field. And so the two sort of mix together near the horizon, and as they go up to infinity, it becomes a superposition of the two. Doesn't really matter. You do some calculation, you get it semi-classically, and then you can go through the whole rigmarole that we just did, but just for quantum emission instead. So we did that, and you get some things where you see there are changes, and it depends on the angular momentum of the black hole, and so on, but you get some nice plots. But that's not really the interesting thing. The fun and interesting part that it's going to sound quite obvious, which is why I'm going to get the embarrassment out of the way in advance and tell you that it took us over 3 years to realize that this was true, is if you've, it's that the extremality bound says that I showed a few slides ago, depends not only on the charge but also on the angular momentum. So if your angular momentum is pretty small, it can be rewritten like this. It's that the mass has to be given by at least the charge plus something that looks like the angular momentum squared. Okay, it's j plus 1 because it's quantum mechanical, but it doesn't really matter. Okay? If you remember your undergraduate quantum mechanics, which we apparently didn't, then there are selection rules. There are selection rules that say you basically have to conserve angular momentum. In particular, they say if you start with angular momentum 0, you emit a photon with angular momentum 1, you can't end up with angular momentum 0, you have to end up with angular momentum 1. But if we start with some state here that's below E breakdown that has angular momentum 0, we try to emit a photon and end up in some state with angular momentum 1, we don't have any states to end up in. So there is no way to emit a single photon from a cold enough black hole and actually end up in some on-zero state. So again, this is very familiar if you do atomic physics. This is a totally standard thing. This is what's called a forbidden transition. The classic example is if you start in the 2s orbital of a hydrogen atom, you want to emit a photon to go down to the 1s orbital, but you're starting with j equals 0, you're ending up with j equals 0, you can't do it. Okay? And it has a huge effect. It's what's called a forbidden transition, and it means that it's incredibly low. So if you start in the 2p orbital, I just Googled these results, so if I'm wrong on them, blame Google. People in the audience who actually know this stuff, but the lifetime is about a nanosecond. So it will just instantaneously decay. Meanwhile, if you start in 2s, it's almost a second. It will sit there before eventually it finds a way to get around this selection rule forbidding it and manage to decay. So how does it do it? Well, it's slightly more complicated in the case of the hydrogen atom, but basically the way it does it is by emitting 2 photons at once. So it emits a photon, is in an off-shell state that it can't really stay in, and it can't really do that, but it pretends to do that, and then it very quickly emits another photon and goes back to j equals 0 again, because the 2 photons can be together in some entangled singlet state where they have no total angular momentum. So this is, I think, a calculation that any self-respecting physicist should have done, but I have no self-respect, so I'm very lucky I had this project, because otherwise I probably would have never have done it. But we had this project, so I have now done it. I can tell you all about it in great detail. All you have to do is go to second order imperturbation theory, and then derive the second order imperturbation theory equivalent of Fermi's golden rule. Okay, and the form of it probably shouldn't shock you. It just looks like you have this 1 over the difference between the on-shell energy and the state it's meant to be in. And then you still have a delta function, but it's just a delta function between the initial and final energies. There's no need for the intermediate state to be on shell, and you get some formula. Okay, so all of this, again, is stuff that we can, in principle, compute with the technology we have. And you do it, and you get this lovely formula here, which I am not going to explain to you the meaning of all these symbols, so don't even ask. But it's some messy, horrible thing involving special functions and so on. But if you go to low enough, what we're really interested in is when the black hole gets really, really cold, how does it scale with the energy? And at that point, a lot of this just becomes numerical integrals that you can do and is boring. And you get some answer that it scales like the energy above extremality to the 17 over 2. So it is incredibly, I cannot emphasize enough how slow this is. It's, the going from a nanosecond to a second with the hydrogen atom, that's with a perturbative expansion, that's the fine structure constant, it's like 1 over 137. We're dealing with perturbative expansions that are like 10 to the minus hundreds. So this is very, very, very slow, but eventually these things get emitted, and there's one thing that it's still faster than, which is the charged particle emission, because that's exponentially slow, and exponentials beat power laws no matter how high the power is in question. And so even though these pairs of photons getting emitted are incredibly slow, there will be an awful lot of them before you ever have a charged particle emitted. But eventually you will. That's the only way it can lose charge, and it will happen. So how does that happen? We're working steadily through this process. So we talked about it a bit before. I just said there's this Schwinger effect. But what really happens is that if I have an electron near a black hole, it experiences 2 forces. It experiences gravitational attraction, wanting to pull it towards the black hole, and it experiences electrostatic repulsion, assuming the black hole is negatively charged. And in general, electromagnetism is a much stronger force than gravity, so it will want to get repelled. Okay, so this potential is negative, except very, very close to the horizon, gravity becomes infinitely strong, because at the horizon it just beats everything, and so then gravity really does become strongest. And so you have this little barrier at the beginning here. Inside this barrier, we have the usual Hawking story of this, or Unruh story of this thermal electrons sitting there wanting to try to get out, but they can't get out because there's the barrier in the way, unless there's some exponentially small probability that one of them just happens to have really high energy. Right? You have some thermal distribution that's exponential in the barrier, but there's some probability it just has enough to roll over this barrier, and then once it's over, it just goes off to infinity, as shown here. So naively, what you'd say is the black hole emits an electron, loses some mass, which is the mass of the electron, but the mass of the electron in Planck units, which is what we're working in, is tiny, so basically it's the same mass as before, and it's lost charge of 1. Okay, so that would seem very reasonable, but it's not true. Actually what happens is this electron gets over the barrier, now has this huge negative potential, it gets accelerated, 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 shoots out at some insane ultra-relativistic speed, its energy is basically the Planck energy, and then it flies off to infinity incredibly fast. So they're a bit like buses, or not quite like buses. You wait for one of these charged particles to get emitted, you wait forever, an exponentially long time, and then eventually one gets emitted rather than 3, but it is one with enough energy to hit you in the face and kill you. So yeah, it still has some, it kicks a punch. So because this ME should really be replaced by Planck mass, it turns out the black hole actually stays pretty close to extremal. It loses almost as much mass as it loses charge. It loses a bit less, so it does get quite a lot hotter, but it stays pretty close to extremal. Of course, so that's the sort of semi-classical story. Of course, given how much the story changed for neutral particle emission with a complete change to the spectrum, we had this diphoton emission rather than single photons, it all went completely different. You might think, and we did, that once you take into account these sort of quantum effects at low temperatures, this is going to change completely. So 4 years ago, we sat down and we started to do the calculation, and it's a very long and complex calculation. So the Schwinger effect is computed by what's called a semi-classical instanton. I'm not going to explain any of this, but experts in the audience may understand. So you take into account the gravitational back reaction of that semi-classical instanton to learn that the electron carries mass, so it changes the shape of the space-time. And if you look at long distances, then that back reaction basically just looks like there's a sort of conical deficit. It looks like the space-time is curved where that instanton is, so it looks like the end tip of a cone. It's a very blunt cone, but it's a cone. Okay? And so you have cones, and then you need to take into account that gravity is quantum mechanical, so you integrate over all geometries, so you end up integrating over something called the moduli space of hyperbolic geometries with defects. So this is something that has won people Fields medals in maths for studying it. You do some very fancy maths. We didn't have to discover this math, so it's easy for us. We just steal their formulas. Actually, we stole formulas from people who stole formulas from them, but you do this thing, you do the calculation, you get an answer that's like changed from the semi-classical answer quite a lot. It's still exponentially small, but it's changed a lot, and you go, great. This is some cool, exciting thing. And then at some point a year down the line, whatever, you realize you slightly screwed up the semi-classical answer, so that's a bit different. Then you realize you screwed up the quantum mechanical answer, there's some complicated stuff there. 3 years and 3/4 down the line, you eventually find that you get exactly the semi-classical rate plus an exponentially small correction. So nothing changes at all. This is the sort of theory equivalent of you do this brilliant, incredibly precise experiment, and you determine incredibly precisely that you have an exactly null result. So that is what it is. Nothing changes this. It's only the neutral radiation that changes. But there is just one more sting in the tail with what happens with the neutral radiation. So the black hole's emitted an electron, and it's now well up above extremality again, and it starts semi-classically radiating its photons and its gravity photons and so on. But something has changed. Something very simple has changed, and that's that an electron is a fermion. So an electron carries half-integer spin. No matter what mode it's in, it carries half-integer spin. So if the black hole started with 0 angular momentum, after emitting the electron, it has half-integer angular momentum. Then it emits lots of photons and gravity photons, but they carry integer angular momentum. And the way the angular momentum rules work means that that doesn't change something from half integer to integer. So the black hole stays half integer, it does all its stuff, but it can never make it down to j equals 0 because j equals 0 is not a half integer. So instead it gets stuck at j equals a half. It can never get below j equals a half. And of course, selection rules, we take a tensor product of a half and 1, we get a half plus 3 over 2. Selection rules allow a photon to be emitted and go from j equals a half to j equals a half. So now we have totally different physics at low energies just because this change of spin from integer to half integer. Now it's all dominated by single photon emission. It cools at this incredibly faster rate and gets much cooler. Okay. Then eventually, of course, you emit another electron and you're back to the bosonic case and eventually the two photons at once. Okay, so I am really basically done. So let me just go through the whole story of what we had here. So initially, we have semi-classical photon and graviphoton emission. Then we get really cold, we get to j equals 0, and we only have this, oh, I have the wrong plot here. Okay. We only have this emission of pairs of photons at a time. We do that for a long time, and then eventually we finally emit an electron, exponential time. But then this time, as we cool down with fermionic, and we settle at j equals a half, we have this far faster rate of cooling. Then we emit again, get back to bosonic, we just cycle back and forth. There's a sort of tick-tock thing between fast and slow cooling. Eventually, after many, many cycles, we get to the point where an extremal black hole has a strong enough electric field that the Schwinger emission isn't suppressed. And then we're back to the story they understood in the 1970s. The black hole discharges such that this field stays roughly the same strength as it gets smaller and smaller, all goes away, until eventually we get down to the last fraction of the second, where I still have absolutely no idea whatsoever how to tell you about what happens. So we've got, after quite a lot of work, to the same position that they got for black holes without a ridiculous charge back in maybe 1977 or so. So that is basically all I have to say. I wanted to leave on some note of like, you know, what we've learned from all of this. I wasn't really sure of the answer, so I just left a few possibilities. But that's basically all I have, so thank you all very much indeed.
Questions for the speaker? Yes.
So when would this come up? Is this the idea that as a black hole evaporates, there's bound to be some charge, and at that point you have to implement some of the physics that you described?
Yeah, absolutely.
Otherwise, the alternative would be the black hole would have zero charge,
yes.
And the previous theory would work.
Yes, so generically, a black hole in any circumstances will have charge. For the black holes, we know the bigger the black hole, the bigger the charge. That is generally true, whatever you make it out of. Because the black hole is big, it will just, you know, the electric fields will be very weak. It will still have random fluctuations in charge. For actual black holes in our universe, they do not have big enough charge for this to happen because they get neutralized pretty well, not perfectly, but pretty well by all the stuff around them. On the other hand, for actual black holes in our universe, none of them are even evaporating because they're all gaining much more energy from stuff falling in than they're losing energy from Hawking radiation. And that would be true even if there was nothing around them because just the cosmic microwave background is still much hotter than any astrophysical black hole that we actually know about. So in terms of direct applications for things that can be seen in our universe, then it's at about the same level actually as Hawking radiation, which is, it's entirely speculative but not impossible. And the speculative way it could be relevant is you can do this whole same story, I didn't, but for magnetic monopoles. And for magnetic monopoles, you don't have some very light electron. And that was why you needed this huge charge to get into this situation. We expect that the lightest magnetic monopoles are, I don't know, Gutt scale, Planck scale, whatever it might be. And so for those things, you will have this physics come into play. So if there are like primordial black holes in our universe that are magnetically charged, then this would actually be relevant physics on potentially relevant timescales. For black holes made out of ordinary matter, it is just as irrelevant as Hawking radiation, which means experimentally completely irrelevant. Even, do these things actually exist, whether we can measure them or not? Basically irrelevant, but theoretically very interesting and relevant. Yeah.
I have a question / prompt.
Yep.
You said that this breakdown that you were talking about at low temperatures was a breakdown of semi-classical gravity,
Yep.
and not, as I think some of the older literature would sometimes put it, of the thermodynamic approximation or some vague statement like that. And that seems like a really important point to me. And you justified it by saying that the geometries that such a decay would interpolate between are just so different from one another. That's highly counterintuitive, given that we're talking about a cold system that's not doing very much anymore, and it might be helpful to explain that a little more.
Yeah, let me make 2 comments. So sort of what I appealed to when I first said that was just there is no solution when you've emitted more energy than you have above extremality, right? So the geometry can't even change that there is no geometry. A comment that, I could have made is that even if you only emit slightly less than extremality, so you go from your geometry, a black hole that's near extremal sort of has some long throat that looks like this. So this is the horizon. This is maybe where the radius of the black hole gets significantly bigger. The cooler I make this black hole, the longer this gets. And if I make the black hole infinitely cold, if I really go down to 0 temperature, then this thing will become infinitely long. So when you start to get down to these regimes, then even emitting 1 photon will want to change the length of this throat, this sort of region outside the horizon, but before you connect to the rest of the universe by some pretty large amount. And so that's basically why, that's why even when the photon being emitted is less than what would take you beyond extremality, then you still need to do quantum gravity even for those photons, because it is still a large change in the geometry. Thank you for a nicely led question to have me explain something that maybe should have been included in the talk. Yep.
Would it explain why the loss of the single electron can make the black hole shorter as it has anything to do with the unknown effect of the fastly accelerating electron?
Yeah, so basically, the simple explanation is we have this bound that in the simplest version says that m is greater than or equal to q, and as in the limit where m goes to q, then the temperature goes to 0, right? And now we're decreasing q by 1 or 1 over 137, depending on our units. And if the change in the mass of the black hole was just the mass of an electron, then that would be tiny in Planck units, right? So we would go from m roughly equal to q to m is roughly equal to q plus 1 over 137, which is now pretty high temperature by comparison. That's not actually right, because this black hole gets shot out incredibly fast. So it's like higher energy than anything has ever been seen, pretty much. It's a Planck energy in just a single particle or close to it. But just you do the calculation, you work out where the electron is likely to be emitted, and you find that the m minus q, there's some lower bound on how small m minus q gets, no matter how small it was before. So even if you started at t equals 0, you end up with some t afterwards that's like, it's very, very cold. We're talking 10 to the minus 100 or so Kelvin, but it's a lot hotter than it was. It doesn't go to 0 no matter how cold it was before. Sorry, say that again?
So the loss of the electron will generally make the difference between m and q.
Yeah, and it's because it decreases q. That's the fundamental effect, is if you decrease q, then the extremality bound, this bound gets lower, and so it gets hotter.
Any other questions? All right, in that case, let's thank our speaker again.